I'll hello. I'll just give it 1 or 2 minutes in case other people are joining, and then we'll start first with the last two questions of week 5, which I had given as practice questions last week, and then we'll proceed to a few practice questions for this week. Okay, so let's get started. So before I go ahead with the questions, in case anybody has any questions from week 5 assignment or any doubts from week 5 content, you can tell me now so I can discuss that as well alongside whatever I'm going to discuss. No questions? Okay. Open 6. Okay. Okay, so these were two questions which I had left. We ran out of time, so we couldn't discuss last week, but they are relevant even for this week, so that's why I left them. That's why I kind of decided that we'll solve it in class today instead of last week. Uh, so, how do we go about this question? Any ideas? I'll give you a few minutes to read it and think. Then you can type your answer in the chat, or you can unmute yourself and speak. How do we normally go about questions in which they've asked us to calculate the MRS? Okay. Um, yes, what is that? How do you do the MRS formula? What is the method? I mean, yes. So, what is the answer in this case then? C. Okay. Yes, that is correct. So, how we do this, I'll just quickly solve this question. So, here we have a function. Let me open the question again. This one is the simpler question. Basically, what we are given is u x y is equal to x plus 2y whole square, right? Uh, So what we need to do is we need to calculate MRS of x comma y, which means ux by uy, where the subscript denotes the partial derivative. So what we are going to do is we'll first calculate ux, which is del u by del x, and you can calculate that. It comes out to be 2 into x plus 2y, uy is del u by del y, 4 into x plus 2y. So here we should put a minus sign here actually, because when you're reporting MRS, we put the negative just to communicate that an increase in one is accompanied by a corresponding decrease in the other. If there is an increase in ux, there has to be a corresponding decrease in uy. So MRS ux uy is equal to minus half, which is what we got as the answer. This is question 8 actually from week 5. Let's go to question 9. This is slightly more interesting one. So the question is actually more than just calculating MRS. Question is asking which of the following statements are true for his preferences. So which of these statements is true? Let's see. Is C the only one which is true, or are there some other statements also which are actually true? So what we do in these cases is usually it's helpful to plot the function, even if you've not been asked a very graphical answer. It's still easier to plot the function. So if I want to plot the indifference curves, I will plot this. This is the function, and the indifference curve is basically like a level curve of the utility function. So it becomes x plus 2y whole square is equal to k, or you can say k square, the same thing. Because we're taking all positive quantities, so it doesn't matter if I call it as k or k square. So k is some positive number, not necessarily integer, but some number. So we can also rewrite this as x plus 2y equal to k, again taking all positive roots, because in the world of economics, we are basically dealing with only positive numbers. We're not dealing with any negative numbers, at least not at this level. So this is basically what kind of a curve? This is a very simple curve, right? This is your, just trying to plot this. So say suppose we take this number as some arbitrary number, x plus 2y is equal to 4, for example. So this is your x and this is your y. Something like that. Okay. You can take any number you like. It just, instead of k, it just helps if you actually have a number there. So it's easier to visualize what the line looks like. So this is a line with a slope of minus half, as we just calculated. This particular function has a constant MRS of minus half, right? Constant MRS itself means that constant MRS, why? Because there is no x or y in this value of MRS. If MRS had x or y in the final answer, it would not be constant MRS, right? It would be changing with the values of x or y or whatever the function came out to be. But when you get a constant MRS, that itself tells you that most likely that function is a line, because a line has constant MRS. Now we calculate this and we draw the line or we draw the indifference curve, which is basically a straight line. So say suppose if this is 4, k is equal to 4, assuming k is equal to 4, then this is 4 and this is 2, right? So now it becomes a little bit easier to visualize which way the substitution is going, right? Because it's easy to say. So this is another way I like to remember it. MRS is in some sense, you can say minus delta y by delta x. So we have minus half over here, right? So if you think of it in this term, delta y by delta x, why? Because it is the slope of this curve, right? MRS is the slope of the indifference curve. So in this case, it's a line, so it's a constant slope. But we can write slope as delta y by delta x. That, I mean, it's very basic fundamental maths, not something complicated. So, but if we write it in those terms, it's a bit easier to relate with which number is delta y and which number is delta x. So if we get this answer, then which is being substituted in which way? Is the consumer giving up 1 unit of y for 2 units of x, or 2 units of x for 1 unit of y? Which way is it happening? Yes, this is the part which is a bit confusing. Yes, that's correct. So then what happens? Let's go back to our question. So is D correct then? P will not be correct, right? Because we just established that Simon is willing to give up 1 unit of y for 2 units of x, right? And in our option, it's the other way around. Now, what other option can be possibly correct? Is there anything else correct, or are all other options wrong? A, yes, great. Because why? We found out that even though this is an x plus 2y whole square, the function is x plus 2y whole square, but it is still, we saw that the actual indifference curve is still a line. And why is that? Because the function we are given, u of xy is equal to x plus 2y whole square, can be seen as a monotonic transformation of x plus 2y. Say suppose there was another function. Assume if v of xy is equal to x plus 2y, then u of xy is equal to v of xy whole square, which is a positive monotonic transformation. Of course, again, in the world of economics, when we say monotonic, we are referring to positive monotonic. And therefore, the basic character of the preferences does not change, even though the function becomes a little bit, different or whatever. So this is something which is very helpful to remember. You could always think of these things in these terms. So now that we know that this is a straight line like this, it means that x and y are substitutes. Therefore, they are not perfect substitutes, but they are substitutes, right? Because, okay, my handwriting is really bad right now. Sorry, I'm not writing at a very proper angle. They're not perfect substitutes. Why? Because for perfect substitutes, the coefficient of both has to be same. So if x and y both had the same coefficient, they would be perfect substitutes. But in this case, it is x plus 2y. It's not x plus y. And it's not 2, even if it were 2x plus 2y, they would still be perfect substitutes because the coefficient is the same. But in this case, it's not so. So they are still substitutes, meaning you are willing to substitute one for the other, but you're not substituting both of them in the same proportion. You're substituting 1 unit of y for 2 units of x. So they are not perfect substitutes, but they are substitutes, which is what the question is basically saying, that x and y are substitutes. So A is also correct. All right, let's go to question 9. This one again tests that same basic fundamental which we were just discussing, which is there are 3 consumers, Sarah, Simon, and Rachel, and they are buying ice creams in 2 flavors, butterscotch and dark chocolate. So now the question is given the other way around, and we have to kind of figure out which one is which one. Okay. So Sarah is willing to forego 2 butterscotch to obtain 1 dark chocolate. Simon is willing to forego 1 butterscotch to obtain 3 dark chocolates. And Rachel is indifferent to dark chocolates but loves butterscotch. All of them do this maintaining the same level of utility. So, which of the following statements is correct? Now, I'll again give you a few minutes to read the question, think it, draw the diagram if you have to, and, and tell me which answers are correct. I'll just mute myself for 2 minutes so you can think. You can type in your answer in the chat if you've solved it. Okay, so I think you are getting confused with the naming. So just assume that dark chocolate you're putting on the x-axis and butterscotch you're putting on the y-axis. That's all it means. When you write MRS of D comma B, it means D is on the x-axis and B is on the y-axis. It's corresponding to MRS x equal to x comma y, sorry. So if that helps, you can try and solve it again if you think that that might help. Okay, yes, I have forgotten what the answer is myself actually. I made this last week, but I think you're correct from what I remember of it. We'll just solve it and check. Okay, any other takers? Otherwise, I'll go ahead and solve it. Okay, let's solve it. So the way we will solve it is basically the same thing we were just doing. Let's go to question 9. Okay, so now I will read it out because I can't have the question and the screen at the same time. But let's first understand how we will approach such questions. The main thing you will do is if you are given 2 3 examples of preferences, you will draw the indifference curve for all of them. Now, before I do that, let's just see what we were doing here first, right? So in this case, when we had calculated the MRS in this previous example, we saw that delta y by delta x is equal to minus half, right? And in that case, what we were getting was 1 unit on y-axis and 2 units on x-axis to maintain a constant utility of 4. Or I mean, you can say 2 and 4, it's basically the same thing. So in this case, what were we doing? We were saying 1 of delta y, 1 is equal to delta y and 2 is equal to delta x. So similarly, we will solve this conundrum also. Say suppose these are Sarah's preferences, okay? But Sarah, now I'm putting dark chocolate on x-axis and butterscotch on y-axis. So which is why I gave MRS D comma B so that you have some basic idea of which one is on which side. So a lot of times the question will not spell it out that you have to put this on this axis and that on y-axis. The question will assume that you know what to do. So if anywhere, if it is given utility function of x comma y or a comma b is equal to this, then that means a is x and b is y. Similarly, if you are given MRS of something something, alpha comma beta whatever, then alpha is x and beta is y, so on and so forth. So from that you can just figure out which one you have to take as good one or which one you have to put on x-axis and which one you put on y-axis. Now question is, Sarah is willing to forego 2 butterscotch, so delta y is equal to 2, and to obtain 1 dark chocolate, delta x is equal to 1. So we'll put 2 here and we'll put 1 here. So assume this is 2, this is 1. So her MRS is equal to what? Minus delta y by delta x is equal to minus 2, right? Now let's move on to which was the next person, Simon. So let's draw a similar diagram and similar logic for Simon. This is Simon's preferences, D and B. Now Simon is willing to forego 1 butterscotch. Again, let's do the same thing here first. Let's put delta y is equal to 1, right? 1 butterscotch to obtain 3 dark chocolates, right? So 1 butterscotch and 3 dark chocolates. You may say that it's not necessary to draw, and I mean, if you're able to kind of connect with it without drawing, that's up to you. But I find it like, it's easier to kind of verify your answer if you have drawn it. If you are making some mistake in calculation and if you draw the diagram, you will more often than not be able to catch your mistake more easily rather than if you don't draw the diagram, because it's easy to kind of get confused sometimes. So here, if you are even more, if you're still confused, what you can do is you can take 1 point here. So from this point, 1 0 comma 1, this point let me put in some other color. So this point is 0 comma 1. Oops, it's too heavy. So this point is 0 comma 1. Let's say from here we come to some point 1 comma 2, or let's say 1 comma 1. It's a bit easier. No, can't be 1 comma. Am I making sense? No, it can't be 1 comma 1. It will have to be 1 comma half or something. Okay. So it's not exactly to scale, so don't go by that. But so now you can see that, if you're traveling down the indifference curve, what is happening? My numbers are actually all messed up, so don't go by the numbers. But if you just want to understand which one is giving up how much, so you can see that there is a decrease in one value y and the other value x. Actually, you should take this based on the equation, which I have not taken. So I'm deleting this in numbers because I think my numbers are off. But just for visual correlation, you can see that you know how much which one is decreasing faster between 2 points. Even if you just don't put any numbers, you can just take these 2 points. Let me redraw that, it's getting messy. So if you travel along the indifference curve, you can see this is delta y and this is delta x. So obviously when you're traveling down the indifference curve, there is a bigger change in x compared with y, which you can see in the diagram just by drawing 2 points on the line. You don't have to do anything else. I was putting numbers, but I realized my numbers were off because you have to follow the equation of the line while mentioning the numbers. So anyway, so hopefully that part is clear. So Simon's MRS is what? -1/3. Now that leaves us with Rachel. Let me look at the question. Rachel is indifferent to dark chocolates, right? But loves butterscotch. Indifferent to dark chocolates means you go this way. Let me take another color. If you go this way, your utility does not change, right? Whereas if for butterscotch, the more you increase butterscotch, the more her happiness is increasing. So Rachel is indifferent to dark chocolates but loves butterscotch, which means what? Which means her indifference curves are one vertical line. I've drawn these pink color arrows to show direction of increase in utility with increase or decrease in a particular good. So in this case, in the case of dark chocolates, I've pointed it in both direction, meaning whether you go this way or you go that way, there is no change in her utility. Indifferent to dark chocolate means there is no change in her utility. Whether you go left or you go right, increase it, decrease it, there's no difference. So what we can see is delta y is equal to some number, say alpha, and delta x is equal to uh, 0, right? Along the indifference curve. Is that so? We're traveling up. If you increase some change, if you make some change in B, then you are getting some increase in utility. And if you change along the x-axis, you're not getting any change in utility. So even if you forget delta y and delta x, this part is a bit confusing, I think. So let's look at it in this way. Is there any change in utility with change in x? No. So this is 0. And is there any change in utility with change in y? Yes, there is some change, or not alpha, let's say something. Say some change. This part, I think, is becoming a bit confusing because we're not changing, we're not foregoing anything. So what we can't really do the delta y delta x very reasonably in this case, because what is happening that she is willing to give up any amount of dark chocolates to increase her butterscotch, but that relation of uh, it's a bit, at least to me, it's a bit abstract to express mathematically. But we know what we are given about utility, right? She's indifferent to dark chocolates, but and dark chocolates is on x-axis, but she loves butterscotch, which means what? That her change in utility with change in the quantity of dark chocolates is 0, whereas there is a positive change in her utility with change in what is the other one? Butterscotch. So MRS is equal to 0, right? I don't know if it's clear to you. I hope it is now clear. So let's go back to the question and see how which ones are correct. So Simon's MRS came out to be -1/3, so that is not correct. Rachel's MRS we just found was 0, and Sarah's MRS we found was -2, right? So B and C are correct. So I think you had the correct answer. Let me open the chat. Yes. So B and C you mentioned, which are correct. Okay, now this was last week's questions, which I'd actually given as homework. Now let's come to this week's question. Although I gave it in last week, actually I realized that you have similar questions even in this week. So no harm done. Okay. So let's go to the next question. Now, in this question, we are given a utility function and we are given the prices of both the goods and we are given the income of the consumer. We have to calculate the optimal consumption bundle. So I'll again give you 2 minutes to read the question, to think, solve it, and then I will discuss it. You can type your answers in the chat once you solve it. Okay. So any ideas how will we solve this? So what happens in the case of the optimal consumption bundle? What do we mean by optimal? Or let's put it another way. When does an optimal consumption bundle actually happen? Also, just a heads up, in case my internet gets connected in between, please stay online for a few minutes. I will log back in as soon as the internet comes back in. It happens very often, so I'm just giving a heads up. Okay. Yes, at the tangency point between indifference curves and the budget line. So tangency meaning both the equations are satisfied at that point, right? The equation of the budget constraint as well as the equation of the indifference curve. So then that means at that point, both the equations are simultaneously true. So then how will we solve? I mean, that was just a starting point. So how do you think we will use that condition to solve this problem? Okay, let's get started with this. This is question 1. Let me write out the basic question. There are two good x and z. The utility function is given by 10x square z. Px is 1 and pz is 20 and y is 300. So sometimes it's just helpful to write down the basics of what information you are given, just without any language, without any literature, just basic numbers of what you are given. Okay, so if you are given px, pz and y, we can write the equation of the budget constraint. Yes, right? So what is budget constraint? Px into x, I'm using, okay, let's use the correct notation, plus pz into z is equal to I. I is given, or y, you can put this as y because they've used the term y. So let's say this is 300 is equal to px is 1, x plus pz is 20 z. So now you already had one equation here for utility function. Now you have a second equation here for the budget constraint. And we just discussed that for optimization for an optimal bundle, both these equations are simultaneously true, or not for, you can say, at the optimal bundle. So what does that mean? It means that I can calculate the value of x from 2 and plug it into 1. It's just two equations in two variables, right? You can substitute the value of one and plug it into the other. And then what we do? We will solve for any one variable. You can choose whichever you like, x or z. I prefer x because it already doesn't have any coefficient. We will solve for x from equation 2, and then we'll plug x back into equation 1. Or you can also solve for z if that's preferable. I don't know, either way it's okay. Let's do z actually. I think it'll be easier to take the yeah, because x is in square, so it'll be easier to take the differential. So from equation 1, you can just write 300 minus x upon 20 from equation 2, sorry, not 1. Right, this is the value of z. Yes, you can do that also, but I'm telling you the general standard method for substitute for optimization. This is how you would normally solve an optimization problem. In this case, neither of the function is very complicated, so you can do it this way also. Sometimes if the functions, and we will come to that example, what you're saying, we'll come to that example. If the relation given, the function given is a bit complicated, then that method, what you're saying, is sometimes a bit easier because you will anyways need to solve for MRS. Okay, let's do it this way since you already know that way. So you know another way of solving it also. So if you're not sure of your answer, you can check it with the other method. So now you can plug in the value of z. See, what I'm doing is basic optimization. Two equations with two variables, both are satisfied. You solve for the value of one variable from one equation, plug it into the other, and then you do the take the differential. So u is what? 10x squared z. 10x squared, and z is this value. Okay, then this is not that complicated. What you get is 10 into 300. Let me write it better. This sounds complicated. Okay, you can of course simplify it further if you need. We don't really need it though. So now we will take the differential of du by dxy, because at that point, for utility to be maximized, du by dx will have to be 0, right? That is basic condition of maximization from differential calculus. So I didn't cancel out the 2 for that reason. Basically, you can just take 2 into 300 by 2 into x minus 3x square by 2. You can cancel out the 2 now. So this is equal to 0. Du by dx is equal to, now if you want to take 2 common, you can take 600x minus 3x squared is equal to 0. Of course, you can simplify it further. 3x you can take as common. 200 minus x equal to 0. which gives you two roots. Therefore, x is equal to 0 or x is equal to 200. Right now, you know the value of x. You can solve for z from this equation, the budget constraint equation, right? 300 is equal to x plus 20z. We know x is 200, so 100 is equal to 20z. Z is equal to 5. Very simple, straightforward method, which works if the functions are not complicated. If the functions are a bit complicated, yeah, you may struggle a little bit. You can still use it, but it's maybe a little bit more time consuming. So what we get is the optimal bundle of x comma z is equal to 200 comma 5. Let's look at the question again. So B is the correct answer. Now it will be nice. I mean, since you mentioned a different method, it's nice. You can probably solve it using that other method also and see what you're getting, if you're getting the same answer or not. You should, of course, get the same answer, but it will just be good practice. Speaking of which, when we come to another question. So this is a very similar looking question. In this, instead of like in this previous, we had 10x square z, where we had like, known coefficient and known exponents. In this question, we actually don't have known coefficients and exponents. There's like, it's a generic form. It's a general form. A b to the power alpha and z to the power of beta, where all you're given is a, alpha, beta are constants, meaning you know the values of a, alpha, and beta. B is burritos and z is pizzas. So you're given the price of burritos, $12, and price of pizzas, PZ, is $10. Y is given as $600. So first of all, what is Bigo's MRS? So this I think is simple enough. You can calculate it. So I'm just muting myself. You can type in the answer in the chat. Okay, one person has answered. Others? I just want to make sure everybody is following what we are discussing. Any other takers? Okay, so since others are not answering, let's solve this and let's see what it comes out to be. So the function we are given is Digo's function, utility function is given as a b to the power of alpha and z to the power of beta. Okay, where a, alpha, beta are constants. And so for MRS, for now, let's keep it this way. You can, of course, write all the other parameters that you're given. PB is given as 12. and PZ is given as 10. Income Y is given as 600. Okay. Now MRS is equal to UX by UY. In this case, this becomes minus U. X is what? B. Okay, I have to write it a bit more neatly. By UZ. The subscript denotes the partial derivative. Okay. So in this case, we're talking about the partial derivative of. Now, if you see that I have not included the negative sign, which means we are just talking about the numerical value. So don't get confused by that. Sometimes the question will be like that. If you are given the answer with the negative sign or without the negative sign, sometimes it may be either way. It depends on the way the question has been framed by the author. So most of these questions I've actually taken from a book. So I've just taken it as is. Okay, now let's calculate del U by del B, which is UB. So A beta B to the power of alpha and Z to the power of beta. So A Z to the power of beta are constant for this particular thing. Alpha B to the power of, okay, I'm just mixing up B and beta for -1, right? This is partial derivative with respect to B. Now let's go to partial derivative with respect to Z or Z, whatever you want to call it. So for this, A B to the power of alpha is constant and beta into Z to the power of beta -1. Beta, beta, whatever you like to call it. The both the American and British and European pronunciations, all of them are simultaneously correct. So MRS is minus, or for the moment, let's remove minus because we know the answer doesn't require us to report it in terms of minus. Let's see what this comes out to be. A alpha B to the power of alpha -1 Z to the power of beta upon A beta B to the power of alpha Z to the power of beta -1. A gets cancelled, alpha by beta, and you can see that there is a one less in exponent in B the numerator and one less in exponent in B in the denominator. So we will get something like this. Not something like this, we will get this. So this is your answer for MRS. And like I said, in this case, we are not riddling the whole exercise with the negative because we're just going with the value of the function. There's a reason why actually the negative is not included here, and we'll just come to that. So this much is clear, I hope. Can we go to the next question, which is related to this one only? So your answer is correct. MRS is alpha Z by beta B. And the next question basically just asks you the optimal bundle. So the next question is in this same scenario where you are given all of this, what is DIGO's optimal bundle? So again, I will give a few minutes to you to solve this and then we'll discuss it. So the calculation may be a bit tedious. I just wanted to show you the method which we use. If if the final answer is too tedious, you can leave it out. For now, you can solve it in your own time because alpha and beta are not given If alpha and beta are given, it becomes a much simpler problem then. So let's go back to our question here. You have MRS is equal to this, and we also know that at the point of optimization, MRS is equal to MRT. I think you guys have not studied MRT yet, but basically MRT is nothing but Px by Py. That is MRT. MRT is just the slope of the budget line. You not, I think you not, I'm not sure, maybe you have, but I think MRT as such is not discussed in this week so far. But either way, even if it's not discussed, there's nothing fancy. It's just this expression which you already know as the slope of the budget line. Right. So at the point of optimization, and you can say tangency, you have this expression which we just calculated for MRS of Z upon beta B is equal to PB by PZ, right? Because that is what it says, MRS equal to MRT. Okay, let's keep it like this. What is PB? 12 and PZ is 10. Okay. So now what you can get is one in terms of the other. You have an expression for Z in terms of B, or the other way around, whichever way you like it. You can again plug that back into your expression for utility and you can optimize it, or you can plug that back into your other equation, the income equation. Let's write the income constraint equation. We haven't written it anywhere, right? So PB into B, PB is 12, B plus 10, Z is equal to Y is 600. So this is your budget constraint equation. Okay. Now you have like different ways of solving this. You can solve it in whichever way you like the most. 10 is equal to 12 beta B by 10 alpha. If you want, you can plug back the value of Z into this budget constraint equation, solve for Z, or you can put this value of Z into the first equation, utility equation, and optimize it with respect to B, take du by dv, equate it to 0, get some value of B, and you can use that. So I'm not solving it because it is too cumbersome. If you want, I can, but I just wanted to leave this as an exercise. If you're not able to solve it, we'll discuss it in the next class. But I mean, do you want to try this on your own or do you want me to solve this here? It's just a bit tedious. I just wanted to show you the method. That's why I took this question. So you should definitely solve it. This is like a general exercise. But if you want, I will leave this for now and we can come back and solve it in the next class if people are having trouble with it. It's just basic substitution and algebra and differentiation. Is it okay? Or do you want me to solve it now? Yes, no, maybe something. Can you solve this or should I solve it now? Is B is equal to, I have not solved it yet. Sorry, I don't know the answer. It's possible that your answer is correct, but I have not solved it. That's why I'm asking. If you want, I can solve it now. Okay, let's try and solve it. You can solve it? Okay, good. So I think you have already solved it. So I will give you this exercise as homework. It's not very complicated. I've already explained how to solve it. So just solve it and see, and I will also solve it and bring the answer with me next time. This time I forgot to bring the answer with me. So I also, even if I had the answer, I just think that it's a good exercise for you to try this question on your own. Okay. So I'm leaving this question here. Solve for B and Z from equation 1 or 2. So you can use either equation. Okay. All right. So here now it's like 5 minutes to 7. We'll just take a 5-10 minute break, and then we will come back and resume the discussion. So in the meantime, I'm just sharing the next question with you. Or let's solve this one first, and then we will go to question 4. Okay. So I'm leaving this on so you can, look at the question and solve it in the meantime. And I'll come back in 5 minutes, and then we'll discuss it again. Okay, so I think at least one person has solved the question. I don't know about the others. It's okay if you're not able to solve it that quickly, but I hope you're following the discussion because that is a bit more important. So, before I go ahead with this question, the other people who have not answered for the questions till now, any problem? If you're having any specific problem in any type of question in concept, please let me know because this is a tutorial class. So, this is the very function of this class to address your doubts and problems. So, if you have some issue, please let me know so I can at least answer you and help you understand. Once again, there is no right or wrong in my class in that sense. In that, I mean, the whole process of learning involves being wrong many times. So it is okay if you're wrong. It's okay if you have realized that you are wrong. It's better than thinking you are right while being wrong, right? So I really do not mind if you ask me any questions in the class or even if you answer wrongly, because that is when I can actually help you understand something. This is like a general thing in all the classes, not just for this particular class or this particular question. Okay, so this is another question of a similar type. In this, the utility function is given to us without any exponent power, so that makes our lives a bit easier. So you have a consumer, Linda, who loves buying shoes and going dancing. So her utility function for pairs of shoes, which is S, and number of times she goes dancing per month, T, is US, comma T is equal to 2 of ST. Then you're given the price of one pair of shoes and one evening for dancing, which is the same, right? The price is the same. Assume she has $1280 to spend on shoes and dancing. So what is, first of all, what is her marginal rate of substitution? And secondly, then we'll come to the optimal bundle. So now we have solved this kind of a function multiple times by now, actually. So hopefully this is not that difficult to solve. Which question is this? 5. Yeah. So I'll come to question 4. Let me first do question 5 and 6, and then I'll come to question 4. So u of s comma t is to st. So most of these questions, by the way, I have taken from the book Perloff. There are some interesting questions in Pindike and Rubenfield also, and I think in workouts in intermediate economics also has some good questions. These were slightly more at the level of discussion which we've had in the coursework. So I took these questions. I think I took Pindike and Rubenfield questions in the last week's course content. So I've taken it from Perloff this week. Just for your reference, in case you want to go back and check the original question. I may have changed the wording a little bit here and there, but mostly they're almost the same. So we know PS is equal to PT is equal to 80, $80. I'm not putting this dollar sign, just leaving the thing simply. And Y is 1280. So MRS is equal to US by UT. Let's put a minus here again. Minus is just to keep things simple, but we know that in this case, again, I'm just going to get rid of the minus because we are going to use this for calculation, and that minus kind of creates a bit of a confusion in the calculations, which is why we often tend to remove it. So US is what? Del U by del S is 2T, and UT is del U by del T, which is 2S, which becomes T by S, right? So the correct answer is A. Next is the um, next is the, sorry, where is the question? Yeah, we need the optimal bundle. So now let's write the budget constraint also. PS into S plus, oops, PT into T is equal to Y. We are given that both are ATS Let me get this a bit. Okay. Plus 80t is equal to 1280, right? That's the question. Yep. Okay. So this is our budget constraint. So you can see now, because we have finally written the equation. What is this equation of? It's the equation of straight line, perfect substitutes. So this may or may not be useful somewhere, but it just means that this is kind of like x plus y is equal to constant. Right now we're putting s here, we're putting t here. If you take 80, if you divide the whole equation by 80, you will get, you know, s plus t equal to some constant k as the, this is, sorry, this is the budget line. I'm so sorry. I mixed it up. Sorry. This is the budget constraint. This is not the utility function. Okay, sorry. This is the budget constraint, but basically budget constraint also, we know that they both have the same prices. So what we get is MRS, if you take MRS equal to MRT in this case, what happens MRS is, oh, sorry, not S, T by S. T by S is equal to MRT is PX by PY, which is 80 by 80, which is equal to 1. So what we get is AT is equal to S, which is a very simple relation. Now the equation becomes quite simple. So it becomes ATS plus ATT is again ATS, which means what, 160 S is equal to 1280. S is equal to, you solve this, most probably you will get 8 or something, right? Let me just confirm. Yeah, so you'll get this as 8. So T is also equal to 8. So okay, so this was again not a very complicated question, but it just requires you to think beyond the language. Let's go back to the question. So here we have a question where, you know, it's not that complicated actually, but it may get a bit confusing if you get lost in the language. Whenever you're given a question of this sort, just assume that, you know, what you are going to do is just find which are the variables, which are the constants, and what is what. So now in this question, instead of this cost Linda $80 to buy new pair of shoes, and she has a total budget for spending on shoes and dancing, instead of this it could have just been something like, you know, instead of money being the constraint, it could have been the number of hours, right? So in this case, instead of say buying, money spent in buying shoes, you can say time spent in buying shoes and time spent in dancing, and she has certain number of hours to dedicate to both, and what is the optimal bundle, right? You have you can have anything as a constraint or anything as a sort of like a similar, which any variable which is acting in the same way as a budget constraint, right? So here we have money, but what we could just as well, this whole problem could just be very similar without too much of change if instead of money we used some other variable like time, right? So instead of money in the same exercise, I'm just improvising a little bit here just to explain what I'm trying to say. So instead of money, time can also be a constraint. Right, so say suppose she has a time limitation. Okay, t is already a variable, so let's keep the variable names the same, of 6 hours, and it takes her uh, oops, sorry, it takes her say 1 hour to buy shoes and 1 hour for going out dancing. I'm just making this up, right? It doesn't necessarily have to be this, but it could be something like this. I'm keeping the same basic character of um, of the equation. So in this case, can we do it? Can we solve the problem? Can we solve the problem using the same kind of logic which we have used so far? So the rest is the same. U of st is 2st. This is given to us, right? Now in this same question, we will calculate the same MRS. MRS is going to be what it was before because utility function is not changed. Now only our budget constraint has changed. So in this case, PS into S plus PT into T is equal to Y. All we have changed is that instead of money, we are taking time as the constraint. And instead of time, it can also be space. It can also be something else, right? So I'm just trying to expand the boundaries of what we are calling as constraint. So you know how they say time is money, things like that, right? So similarly, I think you have similar questions in other parts of your course. So for example, here I have said that she has a total of 6 hours in which she can um, spend, which she can spend on her hobby or whatever. Takes her 1 hour to buy a pair of shoes and takes her 1 hour to go dancing. 1 hour, yeah, something like that. So both have 1 and 1, say suppose coefficient. You get S plus T is equal to 6. Now you can solve for this, of course. You can solve and you will see S comma T will come out to be 3 comma 3, because we already know it's a case of um, T by S comes out to be equal to 1. So then the solution comes out to be 3 hours and 3 hours. Now if it were not that, if it were not so, if the price was different here, so suppose it was 2T, then what would it be? Then it would not be the same. Then you would of course have to make some changes. Here you have MRS is equal to T by S. T by S is equal to PS by PT. And say suppose we have changed the price of T, right? So 1 by 2. So then 2T is equal to S, or you can say S is equal to 2T, whichever way you like to do this. Then what happens? S is equal to 2T plus T is equal to 6. T is equal to 6 by 3, 2, and S is equal to 4, right? I'm just, sorry, I'm making up numbers a lot over here, but I'm just trying to illustrate how the same problem will change with some changes in the values, in the prices or in the preferences. In this case also, like here, if say suppose this function was something else, it would come out as something else. So are you following the discussion? Is this making sense? I hope it is making sense. Okay, so let's go back to question 4. We didn't discuss question 4. Did I have? No, I think I've not added more questions this week. Okay, well, last time actually we didn't have enough time to cover 9 questions, so I brought only 8 questions this time, but I think we have been able to cover it much faster. Okay, let's go to question 4. So what would be the answer here? Okay, one person has answered. Others? Nobody else wants to try? It's a conceptual question. There's nothing to solve in this question. How do you think we sort of go about these type of questions? What we are trying to calculate in this particular question is how much sort of you're trying to understand what, like, this is a sort of a crude expression, but what you call as bang for the buck, right? You are getting the marginal utility of good A, the marginal utility of good A and its proportion in terms of its price versus marginal utility of good B and its ratio to its price. So for example, I'm getting 5 units of utility from consuming coffee, and coffee costs, say, one increase in, say, suppose marginal utility is what? Increase in utility for, say, you can say unit change in consumption of that particular good. So if I take 1 cup of coffee, my utility increases by 5. So my marginal utility for coffee is 5. But the price of coffee is what? Say it's 20. So 5 by 20 is my marginal utility. Let me write that down, because I'll forget what I was saying. Oops, sorry. Let's go to question 4. I'll come to the actual question 4. Let's say my marginal utility for coffee is equal to 5 and price of coffee is equal to, say, 20, right? Similarly, my marginal utility for tea is, say, 5 and price of tea is equal to 10. So what we're trying to understand is which one is giving us more, how should you say, I can't think of a better expression actually, which one of the two is giving me more bang for the buck. It's a crude American expression. Bang for the buck means how much you're getting for every dollar or every penny or every rupee which you spend. So here in this case, MUC by PC is equal to what? 5 by 20, 1 by 4, or 1 to 5, whichever way you like it. MUT by PT is equal to 5 by 10 is equal to half. So which one should I consume more of? T, right? Because I'm getting more value out of for every penny or every rupee I spend on tea. So in this case, you have mine is greater than, and this is kind of what you'll see happening in life. This is, I mean, I think Professor Vimal has explained it mathematically in the lectures. It's good if you review that. But even if you don't get into the maths and stuff like that, that's why I took this example of tea and coffee. If my valuation of two things or my utility gained from 1 unit consumption of two things is the same, but the price of one is more and the price of the other is less, I will consume the one which costs lesser, right? And this is kind of how we take decisions every day. This is the basic reasoning for decision making in an everyday setting, which has been kind of very nicely articulated in a mathematical structure. Now, if you just think about it, when you're buying stuff in the market or on Amazon or wherever, if there are two, three goods which are almost similar or whose with the valuation for which is similar to you, right? Say suppose you're just trying to buy some item on Amazon, and there are like three or five of them over there, all look very similar, or you are equally you like all of them almost the same. There's none which is exceptionally better or exceptionally worse. Or you can, another way of saying that, mathematically maybe more appropriate way of saying that, is your marginal utility is the same for consuming 1 unit of any of those goods. Then what is the deciding factor? The price. So if five goods are giving me the same marginal utility and the price of one is more and the price of second is less, and then so on and so forth, I'll buy the one which costs the least. It gives me the maximum bang for the buck, right? So that is what this question is asking you. Now in this case, I have taken marginal utility as the same for tea and coffee, but it need not be the same. It could be something else. But at the end of the day, this expression is what you're looking at when you're making a buying decision. So when you are, even if your marginal valuation or marginal utility from consumption of two goods is not exactly the same, how do you reason whether you should buy one or the other? Okay, this one is nicer, or it looks nicer, or it may be a bit better quality, but is it really worth the price at which it is being sold? Say suppose there is one item which is priced at rupees 1000 and it serves the function decently well, and there is another item which is a bit nicer quality, a bit better to look at, maybe something nicer, you'll be happier to have it. Marginal utility is more for the second one, but say the price is 2000, price is just double. So how are you reasoning in your head? Reasoning in that same way, right? That is this second good really worth that price differential which it has? I mean, is it really worth that amount of money? That sort of, is it worth this price, is kind of what we are discussing. So this is what we're talking about. So in this case, when, say suppose this is an optimization problem or a consumption bundle problem, right? This is, say suppose, green difference curve, and let's say this is coffee and this is tea. Okay, so in this case, this is an indifference curve. This is a set of indifference curves, say suppose. This is too shaky to be a curve. These are the indifference curves, and utility is increasing in this direction. Okay, so now what we're trying to figure out is that which one should the person consume more of, and also why. So why will the person consume one or the other more? See, we are not talking about which one will he consume alone, because this is like a choice between two goods, right? We're not saying that the person is indifferent to coffee. The person is getting some valuation from coffee also, right? But not in the same proportion when you consider the price also. So what we are looking at is, another way of looking at this is MUT by MUC is greater than PT by PC, right? So this is what is this? MRS, and this is what? MRT, or slope of the budget line. Say suppose your budget line is something like this, and let me erase this. Okay, very convincing. Okay, so this looks almost tangential. Are you able to hear me? Am I visible and audible? Oops, I think my internet is. Okay, my internet got disconnected as I had warned in the beginning. Just give me a moment. Let me join back in. Sorry, I'm just trying to log back in from my iPad. Okay. Okay, so I hope you can see my screen. So am I audible and visible, and is my screen visible to everybody? Just checking because the internet was not very helpful. Okay, thank you. So what were we discussing? We were talking about marginal utility and price, and I was talking about what I mean by bang for the buck. So sorry, I really like that expression. It's kind of like one expression which has very little other equivalent expression in the language. Okay, so this is where we have our indifference curves, and this blue thing is the budget constraint line. Let's make it a bit thicker. Yeah, this is a bit better. Okay, so what we were talking about was just the difference in marginal utility and the price between comparison between two goods. Now, what we discussed, if you remember our discussion, what we have been doing all throughout this entire tutorial, actually, what we have been doing is at optimal bundle, we have been saying MRS is equal to MRT, which is basically nothing but the slope of the indifference curve and slope of the budget constraint. That's mathematically speaking. Of course, we know what it means otherwise. I was just explaining when I think at that point I got disconnected that the person, consumer in this example, is not indifferent to coffee. I've just taken example of coffee and tea. You can take good A and B, whichever way you like. I just think it's a bit easier to relate to like this. So the person is not indifferent to coffee. If the person was indifferent to coffee, what would happen? Marginal utility of coffee would be zero. Does that make sense? Because if you are indifferent to something, consumption of that thing is not bringing you any utility. That is what indifferent means, right? In the sense of preferences. I'm not talking about indifference curves. Indifference curves are something else. In the world of consumer preferences, marginal utility of that particular good will be zero. In this case, we are given marginal utility for coffee is equal to 5. You can call this as mu. See here, right? Is equal to PC. Let's put the notation in. So in this case, we are given some utility for coffee. We are getting some utility for consumption of coffee. It is just that it costs a lot more. So I'm not going to consume it in that same proportion, or I'm not consuming it as much as tea. So, but it is increasing my utility. So the purpose is that until the marginal utility of one with respect to the other becomes equal, I will keep consuming one or the other good, right? That is what optimization, or that is what consumer choice is all about. So in this diagram, if you see, my utility is increasing in this direction, right? At this point, I'm at, use some other color. At this point, if I'm at some level of utility, if increasing coffee and or increasing tea is increasing my utility, I will until I reach this point. I would like to reach this, let's use green. I would like to reach this points also, but the problem is they are not within my uh, budget. I can't afford them. So what I'll do, I will be content with just consuming this big pink point. I don't know if you can see it. That point of tangency between the budget and the indifference curve. That is the maximum utility I can achieve with my budget, because budget is not in my hands, right? It's exogenous to whatever we are doing. Which means that if I'm at this point, I will increase my consumption of both the goods, because you see, in consumption of both is increasing my utility, just not in the same proportion when you consider the price. Actually, even the utility is increasing in the same proportion, but when you factor it against the price, it's not the same, right? So you will increase your consumption of both tea and coffee. I'm answering this part because I think somebody said that they will not consume coffee at all. They will consume not consume that good at all. They'll consume only the other good, which is not the case. If we knew that there is no utility from consuming that good, then they would. So in our actual question, let's go back to the question which we already had. So in this question, what we are given is that MUA by PA is greater than MUB by PB, but MUB is not zero. Unless MUB is zero, the person will consume B, but it's easier for the person to consume A, right? So the answer will be the consumer should consume more of good A and less of good B, but they will consume both the goods, right? Is the explanation clear to everybody? Any questions? No? Okay, so I think I am actually done with my set of questions which I brought to class. Yeah. I last time we couldn't complete 8 questions, but today we completed 8 questions in much shorter time. So this is just a kind of a difference calculation of time. So we still have around 20 minutes left. Any of you have any question of yours you want to ask, or if there is any question from week 5 assignment, we can discuss that also. So let me do that. Actually, let's see week 5 assignment. There is any question which I think is worthy of discussion. So week 5, was everything clear? Any doubts you guys have? You're asking the utility function, does it matter? If the goods were perfect substitutes, wouldn't we get a corner solution? If the goods were perfect substitutes, it just means that um, that their marginal utility, like their MRS, would be constant. It doesn't necessarily mean that you will get a corner solution. 1 minute, let me just think over that a bit. So let's draw the case for perfect substitutes. So if they were perfect substitutes, you would get indifference curves like this. So, oops, what did I do? So remember, indifference curves, I'm drawing only 3, 4, but there are infinite number of lines for indifference curves. So let's take the same thing as we took before, coffee and tea. Okay, these are your indifference curves, and somewhere, let's take the same kind of thing. This is your budget constraint. Okay, now I have drawn it like this, but budget constraint doesn't actually have to be parallel to your indifference curves. It could be something like this, right? Or depending on the prices again, could be something like this. This could be your budget constraint. Okay, so one common mistake is when we're not given any function, we kind of assume that if they are both straight lines, they're both parallel or they are kind of superimposed over each other, which is not usually the case. In very rare cases, that is the case, but it is not the case here. So if the price for both is the same, then only, and both are perfect substitutes, then of course you will get two lines. Indifference curve and budget constraint will be superimposed. But in this case, the point of tangency is the point of intersection because they're both straight lines, and straight lines can only intersect. They cannot really, there's no other point of tangency, right? So in this, actually, let me not take this complicated example. Let's for the moment assume, because we'll have to go into linear programming in a little bit if we take it that way. Let's just forget about the budget constraint for now. Let's just look at the indifference curves. Now, in this case, all we know is that marginal utility of both goods is the same, and the MRS is the same. MRS is, sorry, not same. MRS is constant. So all we know is that the MRS is constant for the two goods if they are perfect substitutes. Perfect substitutes means what? X plus Y is equal to K. But even in that, what you have is there are different straight lines for different values of K. Say suppose this is K is equal to 8, K is equal to 4, K is equal to 2, like that, right? So what we are saying is that in this case, the consumer, what we are given is mu C by PC and mu T by PT. These are the two values we are given. So as long as uh, uh, okay, I think I get your question now. You won't get a corner solution. In if you are given MUC by PC is greater than MUT by PT, what will happen is the person will keep consuming this and not consume this until your budget constraint is satisfied, which is at this point, like I was drawing. So see, in this case, when you have a budget constraint, which is something like this, you will have two cases. We have not studied that part right now. That's why I think it's a bit confusing for you. So in this, in this kind of an example, you can see that there is only an intersection. There is no, there is no overlap. There will be two regions basically in this kind of a case. Let me draw with some other color. So here, up till this point, say suppose this is a point of intersection E. This is a point of intersection E. Up till here, you will have one set of optimization bundle, which is here, and then after this, there will be a second set of optimization bundle. So it is not going to be a corner solution, but it will not be just one optimized bundle, right? Like you will have an entire region, and I'm not going into that problem right now because that is not something which is part of your coursework. So don't worry about that. But all I can say is that you will not be given a question like that, hopefully. So let's look at this example which is relatively simpler example. Say suppose this is xy is equal to u is equal to some value, right? Then you have something like this. In all these cases, your budget constraint is actually going to be tangent. It's not going to intersect. It's going to be actually tangent here. And in this case, what you will get is what I'm talking about, right? So suppose these are other indifference curves, you will keep increasing your consumption. What we're talking about is in what direction are you increasing your consumption? From here, from this point, you want to reach this point. How are you going to reach that point is what we're talking about. In what proportion are you consuming one good versus the other good? So say suppose this is X, this is Y. In what proportion are you consuming X? In what proportion are you consuming Y to reach that optimized bundle? Is that, I don't know if I was able to answer you. Does that make any sense? Okay, great. So I think this covers most of it. And this kind of a case is actually solved using linear programming, and I think I don't know if it is there in your coursework. This is not it's not solved using the usual optimization method which we use, which is why I'm not delving into it. I don't want to confuse you people. But in this kind of a case, all the question is asking is that how are you going to like see you're increasing your consumption of both the goods. It is just that you're going to increase the consumption of one more than the other, and in which when that happens you will keep increasing it until you reach the point where your MUC by PC will be equal to MUT by PT, because this is the condition for tangency, right? This is the condition for tangency. And this, of course, is going to happen only if MUC and MUT are not constant. In a straight line, you know that they are constant, right? So in this kind of a thing will not arise. So we are not talking about that straight line condition here. Okay, and in the straight line case also, I think at least if you are given that kind of a problem with perfect substitutes, hopefully you will be given the case where the budget line is superimposing on the indifference curve. You're not, I don't think you'll be given the case where they're intersecting. Okay, so I think if that's it, if you don't have any further questions, I would end the class here. And in the next class, we can discuss any doubts you have from week 6, plus from the week 6 assignment, that is, plus the course content from week 7. So just once again, a reminder that I upload all the slides that I bring to the class and the class notes. I upload it all to a folder that is linked to the tracking sheet which you have um, on your portal. But just in case you are not able to find it, I think many people have trouble finding that. So I'm posting the link here once again. If you want to go back and look at the slides or the class notes or something, you can do that here. Oh, one more thing. Yeah. Okay, let's discuss that in the next class. That's kind of small thing, but yeah, I'll need some time to discuss that. I didn't bring the slides for that. So okay, so then I think we can end the class here, and I'll see you again in the next class. Thank you.